What if the greatest archaeological treasures of our century are not hidden beneath layers of soil, but drifting silently through the void above us? For millennia, we believed Earth stood apart, an island world, quarantined by the unimaginable distances between stars. That illusion fractured in 2017 when a strange object hurtled past at 87,000 kilometers per hour, defying every expectation. It was not alone. Others followed enigmatic shapes that moved unlike any comet or asteroid we had ever charted. They twisted the rules of motion, accelerating without exhaust, surviving million-year odysseys as if sculpted to endure. They emerged from every compass point of the galaxy, appearing so often that even probability itself seemed to bend beneath the weight of their arrivals. And now, as 3I Atlas arcs toward its closest embrace with the Sun, the mystery sharpens. This is no isolated anomaly, no one-off curiosity like Oumuamua once seemed. Instead, Atlas reframes that first encounter as a fragment of something larger, a pattern, a revelation unfolding across cosmic time. Each pass of these visitors erodes the comfort of old certainties, demanding that we consider the unthinkable, that the galaxy is speaking in artifacts, not whispers. So we stand at the threshold of wonder, gazing upward. The story is not buried in ruins beneath our feet, but inscribed in trajectories of stone and ice that cut across the stars. Tonight, as Atlas blazes near the Sun, the puzzle deepens and the adventure begins. Picture this. Midnight settles over the Haleakala Observatory in Hawaii, where the silence is broken only by the steady hum of cooling fans and the faint clicks of hard drives storing the night's harvest of starlight. On the monitors, the universe looks deceptively simple. Countless points of light pinned against a canvas of black. Astronomers are trained to trust these patterns. Stars do not stray. Planets glee along predictable ellipses. Even comets and asteroids, unruly as they appear, follow the gravitational choreography that has endured for billions of years. But on the 19th of October 2017, the sky betrayed expectation. The Pan-STARRS telescope captured a fleeting point of light that moved too swiftly, too strangely, to belong here. It was not orbiting our Sun in the quiet way every other local body does. Instead, it was cutting across space as though passing through on a mission of its own. When the first calculations rolled in, jaws tightened. Its trajectory was hyperbolic, not bound but unbound proof that it had come from elsewhere and would never return. Its speed relative to the Sun, 26 kilometers per second, exceeded anything we thought natural for an object born in our cosmic neighborhood. Within hours, the global astronomy community erupted. Emergency requests surged across telescope networks, each racing to glimpse this stranger before it vanished into the abyss. On social media, speculation multiplied. News anchors stumbled through its Hawaiian name, Oumuamua, scout, messenger. The label was apt, but it carried unsettling weight. As telescopes tracked it, assumptions began to splinter. This was not the rounded rock or icy body everyone expected. Its brightness shifted tenfold as it tumbled, revealing an elongated form like a cosmic spear or cigar, nearly 800 meters long yet scarcely 80 meters wide, spinning end over end. Its surface gleamed in ways that hinted at unusual chemistry, or perhaps something engineered. Some scientists whispered possibilities that felt more like science fiction than astrophysics. What if this object was not natural at all? Then came the most unnerving discovery. As Oumuamua moved away from the Sun, it accelerated ever so slightly. Comets accelerate when volatile gases burst into jets under solar heat, but no such outgassing was visible here. The effect was real, but the mechanism was missing. Dr. Robert Werrick, who first spotted the anomaly, later confessed, You think the computer made an error. Objects just don't move like this in our solar system. Yet the computer was right. The cosmos had delivered something unprecedented. Explanations bloomed. Perhaps Oumuamua was debris, cast out long ago from a distant planetary system, flung into interstellar exile by gravitational chaos around an alien Sunday that fit the mathematics. Yet the odds of catching such a fragment during the brief blink of humanity's observational era seemed absurdly slim. Unless, of course, such visitors were common, their arrivals not miracles but inevitabilities. By the time Oumuamua slipped beyond our strongest telescopes, bound for Pegasus at 38 kilometers per second, it had left a trail of upheaval. Observatories reoriented priorities. Sky surveys fine-tuned algorithms to catch more of these hyperbolic wanderers. Funding flowed toward the once dismissed idea that interstellar objects could and would enter our cosmic backyard. The discovery marked a pivot point. The universe was no longer a static backdrop. It was dynamic, porous, alive with messengers. For the public, the story landed like a spark on dry tinder. Could this elongated traveler be technology, perhaps a derelict probe or solar sail, a relic drifting from a civilization unimaginably old? Mainstream astronomers resisted that leap, but the silence of certainty had already been broken. The very fact that such a hypothesis was whispered in academic halls revealed how disruptive this visitor had been. What lingers most is not just the anomaly of shape or acceleration, but the sense of perspective it forced upon us. For centuries, humanity looked skyward, believing interstellar space was an empty gulf. Oumuamua whispered otherwise. It suggested that the galaxy is threaded with wanderers, fragments of shattered worlds, survivors of stellar violence, perhaps even artifacts of intelligence. Each carries a history written not in words, but in trajectories and physics, waiting for us to notice. The messenger from afar delivered a simple but profound truth. The space between stars is not empty. It is a highway, and travelers use it. Some are chunks of rock and ice, survivors of planetary upheavals. Others may be stranger still. Humanity had stumbled upon the first clear sign, and though Oumuamua vanished into darkness, its legacy endures in the shift of our gaze. Now we scan the skies differently, not asking if another visitor will come, but when. And when it does, we will be ready to read the story it carries. The age of interstellar archaeology has begun, and the universe has already written the prologue. Part 2. The Day the Sky Changed. The transformation of our understanding did not creep upon us gradually, like the slow erosion of rock by wind and tide. It happened all at once, an instant etched into astronomical history. A robotic telescope atop a dormant volcano in Hawaii captured a frame of data, and with it, humanity's relationship to the cosmos shifted forever. It was the 19th of October, 2017, 2:20 a.m. local time. The Pan-STARRS. One telescope on Haleakala completed another routine sweep of the heavens, photographing a patch of sky in the constellation Cancer. The image, like countless before it, contained roughly 60,000 stars. Most of those points of light had traveled millions of years to reach that mountain peak, their photons whispering ancient stories into our detectors. But hidden among them was something entirely different, a sliver of sunlight reflected off a body that had never belonged to our Sunday. At first, it nearly slipped away. The automated software flagged the object as a near-Earth asteroid, ordinary, forgettable. Our solar system is crowded with such fragments, rocky debris left over from its violent birth 4.6 billion years ago. But when Dr. Robert Werrick, reviewing the night's observations at the University of Hawaii, checked the data, he felt the dissonance immediately. The object was moving too quickly. its trajectory was wrong. Early calculations whispered the unthinkable. This thing was not from here. Most astronomers, confronted with such a result, would have assumed an error in code. Yet the error was not in the machine, it was in our assumptions. The object received a temporary designation, A, divided by 2017 U1. The label was bland, bureaucratic, giving no hint of the extraordinary reality behind it. But within 48 hours, the blandness evaporated. Observations confirmed that the visitor's orbit was hyperbolic, its eccentricity greater than 1. In the language of orbital mechanics, that single digit spelled revelation. The object was unbound, slipping past the sun, never to return. It was a messenger from another star system. The response was instantaneous. Astronomers submitted emergency requests to every major telescope on Earth. Time reserved for long-planned projects was sacrificed. The Hubble Space Telescope, the Very Large Telescope in Chile, Gemini in Hawaii, all turned their gaze toward this fleeting traveler. The window would be short, mere weeks before it faded into invisibility. Every moment mattered, and with every new observation, the mystery grew stranger. The object did not resemble a comet or asteroid. Its brightness waxed and waned by a factor of 10 over an 8-hour rotation, signaling an elongated form. The best models suggested a shape unlike anything ever seen, perhaps 800 meters long, yet only 80 meters across, as though a cosmic cigar were tumbling through space. The aspect ratio defied natural categories. Some imagined a javelin, others a flattened shard. The comparisons were inadequate. It was unique. Radio telescopes were enlisted, ears pressed against the void, searching for artificial signals. SETI researchers joined in, unwilling to ignore even the faintest chance. Silence answered. Yet the silence did not resolve the unease. Then came the anomaly that deepened everything. As the visitor drifted away from the sun, its trajectory betrayed a subtle acceleration. Such non-gravitational nudges are common among comets. Jets of gas sublimating under solar heat act as tiny thrusters. But no coma, no tail, no outgassing could be found here. Spectroscopy showed no trace of water vapor, no familiar chemistry. The object sped up without explanation, as if pulled by an invisible hand. Its surface appeared unusually red, consistent with organic compounds bombarded by cosmic radiation over eons. Yet despite what must have been a million-year journey through interstellar space, the body showed none of the scars of endless bombardment. It remained intact, enigmatic, unwilling to reveal its origins. Dr. Alan Fitzsimmons of Queen's University Belfast voiced the collective bewilderment. Every time we pointed a new instrument at this thing, it became stranger. We kept expecting it to behave like a comet or asteroid, but it refused to follow the script. The world outside the observatories took notice. Within days, headlines carried the name Oumuamua, Hawaiian for scout or messenger. It captured imaginations across the planet. Some asked whether it might be a shard of an alien world, torn loose by some ancient catastrophe. Others dared whisper, could it be an artifact, technology adrift, perhaps even a probe? The scientific establishment urged restraint. Extraordinary claims demanded extraordinary evidence, and natural explanations, however incomplete, remained safer ground. Perhaps Oumuamua was made of materials unknown in our system. Perhaps its bizarre form was the outcome of countless collisions and ejections. But one question could not be ignored. If interstellar debris was truly common, why had we never seen one before? Decades of sky surveys had catalogued hundreds of thousands of comets and asteroids, yet none had betrayed origins beyond the Sunday. Was this luck, an improbable alignment of timing and technology? Or was it a clue that such visitors are not rare at all, but numerous, streaming through our system like driftwood in a cosmic current. The implications were staggering. If Oumuamua was typical, then fragments from alien worlds were constantly flowing past us, undetected, silent emissaries of other suns. Perhaps every year, perhaps every month, such pieces entered our neighborhood, carrying chemical fingerprints of their birthplaces, clues to planetary systems we have yet to discover. Oumuamua remained visible for only 11 weeks, yet in that span it transformed astronomy. Funding agencies, once skeptical, began to support research into interstellar detection. New surveys were designed explicitly to find such wanderers. Algorithms were rewritten to identify hyperbolic trajectories. The paradigm had shifted. The space between stars was not empty, but alive with travelers. By December, the visitor had slipped beyond our reach, bound toward the constellation Pegasus at 38 kilometers per second relative to the Sunday. Yet its absence weighed as heavily as its presence. In leaving, it had exposed the permeability of our solar system, the truth that we are not isolated but enmeshed in a galactic ecosystem. Material flows in and out, debris crossing light years to deliver itself uninvited to our doorstep. The realization was humbling. We had imagined ourselves observers, waiting for messages sent intentionally from distant civilizations. Instead, the universe had shown us a different kind of communication, messengers written not in radio waves but in physics, chemistry, and the silence of motion. Oumuamua was the first, but almost certainly not the last. If billions of planetary systems exist across the galaxy, each shedding fragments over cosmic time, then the skies above are filled with wanderers. The 19th of October, 2017 was not merely a night of discovery. It was the night the sky changed, when humanity understood that the void was not void at all. Somewhere, far beyond Pluto's orbit, Oumuamua continues its ancient voyage. It carries with it no answers, only questions, echoing across the interstellar dark. And those questions remain with us. What else is out there? How many more messengers will pass unnoticed? And are we ready to confront what they might reveal about the galaxy we call home? Part 3. The impossible shape. The numbers didn't add up. That was the first thing astronomers realized when they tried to model Oumuamua's light curve. In space, rotating bodies usually show mild variations in brightness, perhaps 20 or 30% as they spin and present different surfaces. But this object was following no such script. Every 8.26 hours, its brightness swung by a factor of 10. It dimmed almost to invisibility, then blazed tenfold brighter, then dimmed again, all with a regularity that seemed mechanical. This was not the gentle flicker of a potato-shaped asteroid or the uneven glint of a broken comet. It was something else, an interstellar enigma that seemed engineered by geometry itself. Dr. Karen Meach of the University of Hawaii, leading the international team poring over the data, recalled the moment vividly. When we first saw the light curve, several of us assumed it was an error in reduction. Objects don't form with aspect ratios this extreme. But the numbers held. Even conservative models suggested Oumuamua was at least 6 times longer than wide. Others pushed the ratio higher, perhaps 10 to 1. Imagine a football field stretched to its full length but scarcely 10 yards across. No known mechanism in planetary science could create such a thing, let alone preserve it across the violence of interstellar travel. The rotation compounded the strangeness. Most asteroids and comets spin neatly around their shortest axis, like tops wobbling but ultimately stabilizing. Oumuamua refused such order. It was tumbling chaotically in what scientists call non-principal axis rotation cosmic gymnastics, an end-over-end tumble across space. Such a motion implied either a recent collision or an interior of baffling complexity, maybe hollow, maybe uneven in density, maybe artificial. Its surface only deepened the puzzle. Spectroscopy showed a dark, reddish hue, the telltale signature of organic compounds baked for millions of years by cosmic rays. That suggested an ancient body, possibly older than our solar system itself. Yet its structure appeared pristine, not battered or fractured as one would expect from eons of micrometeorite impacts. Its stoicism hinted at something designed for endurance. Thermal data raised further alarms. As it swung near the sun, it should have warmed enough to sublimate ice, spouting gas jets like any comet, leaving a halo or tail. Instead, nothing. Oumuamua stayed inert. No coma, no vapor trails, no volatile bleed-off. And yet, paradoxically, its path betrayed acceleration. Subtle, measurable, 0.25 millimeters per second squared. Tiny, yes, but unmistakable. Multiple observatories confirmed it. Something was pushing it outward, invisibly. Dr. Marco Michelli of the European Space Agency summarized the dilemma. We're seeing acceleration that requires a force, but we cannot identify the engine. It's like watching a car speed up without hearing or seeing any motor. Hypotheses swarmed. Some suggested ultra-faint outgassing, too tenuous to detect. Others proposed exotic materials, perhaps hydrogen ice sublimating invisibly. More radical models invoked fractal ices or nitrogen shards ejected from alien worlds. And then, from the edge of orthodoxy, a bolder voice rose. What if it was a light sail? Dr. Avi Loeb of Harvard argued that the acceleration fit exactly what solar radiation pressure would impart on a thin, broad structure. The extreme elongation, he suggested, might not be incidental but intentional, maximizing exposure to starlight. Perhaps Oumuamua was a derelict craft, a probe or relic from another civilization. When confronted with the unprecedented, Loeb insisted, we must consider all possibilities, even those that challenge our preconceptions. The debate tore through the community. Mainstream astronomers clung to natural explanations, hydrogen icebergs, exotic collisions, tidal disruptions, yet each demanded finely tuned scenarios and physics unverified in our solar system. The artificial hypothesis was speculative, but it explained the data with fewer contortions. Still, without extraordinary evidence radio signals, close-up imaging science could not cross that threshold. As the object slipped away, questions piled up. How could such an extreme shape remain intact under the stresses of tumbling? What invisible force pushed it sunward? If this was typical of interstellar debris, how many others had slipped past unnoticed? Computer simulations tried to reconstruct its origins. Fragments torn from planets by tidal shear near giant stars, shards launched from stellar nurseries, relics carved by collisions in dense clusters, none satisfied fully. Each model left contradictions unresolved. Dr. Robert Werrick, who first spotted the object, summed it bluntly. We've learned more from this single visitor than decades of theory. Mostly, we've learned how much we don't know. By the time Oumuamua faded beyond detection, bound for Pegasus at nearly 40 kilometers per second, it had already altered astronomy. It showed us that interstellar space is seeded with wanderers that break rules we thought inviolable. Its impossible shape forced us to imagine new processes or new artifices beyond our experience. And in its silence lay a message. The cosmos is stranger than we dreamed. Some visitors may be shards of lost worlds. Some may be something else entirely. What Oumuamua proved, above all, was that we are unprepared for what drifts between the stars. The cosmic cigar tumbled into the dark, carrying our unease and wonder with it. In its wake, The scientific community was left humbled, grasping at fragments of explanation and staring into a universe that had just grown immeasurably larger, stranger, and more alive. Part 4. A New Cosmic Era. The response to Oumuamua was not hesitation, not denial, but a quiet revolution. Within months of its departure, astronomy itself had changed. What had been considered speculative, borderline fringe was suddenly a priority at the highest levels of science. Emergency meetings convened at observatories from Hawaii to Chile, from Arizona to the Canary Islands. Funding boards, which only a year earlier had laughed off proposals to study interstellar debris, now signed off on multi-million-dollar projects. The message was simple, humbling, undeniable. Humanity had been caught off guard, and it could not happen again. The Catalina Sky Survey in Arizona was among the first to react. Its algorithms, once fine-tuned to hunt Earth-threatening asteroids, were rewritten to detect the faint mathematical signatures of hyperbolic motion paths that whispered of origins beyond the Sunday. Soon after, the Linear program in New Mexico followed suit, and NASA's Neowise Space Telescope adopted similar upgrades. Yet the most ambitious transformation came from Chile, where the Vera C. Rubin Observatory was still under construction. Originally conceived to map the heavens in unprecedented detail, the project quietly expanded its mandate. It would become humanity's sentinel for interstellar visitors. Once operational, Rubin would scan the entire sky every few nights. Its torrents of data filtered through artificial intelligence trained specifically to spot the subtle strangeness of objects from other stars. Dr. Mario Jurich of the University of Washington explained the scope. We're talking about finding needles in a haystack the size of the observable universe, but Oumuamua showed us that these needles are real, and they're passing through our neighborhood more often than we thought. Mathematics justified the urgency. If Oumuamua was not a singular oddity, but representative of a vast unseen population, then dozens, perhaps hundreds, of such objects might sweep through the solar system every year. Most would be faint, lost in the dark, but some large enough, bright enough, should be within reach. Where once astronomers predicted one detection per decade, now the numbers demanded a new world view. Interstellar space, far from empty, seemed crowded. The response became global. The European Space Agency fast-tracked a successor to the Gaia mission, mapping stellar motions with exquisite precision to trace the origins of visitors. NASA's Planetary Defense Coordination Office expanded its charter, no longer limited to guarding Earth, but also to cataloging wanderers from other suns. Even amateur astronomers were enlisted, their backyard telescopes linked by new software tools that allowed citizen scientists to contribute detections. Technology itself had to evolve. Interstellar travelers are unlike local comets or asteroids. They flash across the solar system on hyperbolic arcs, detectable only for weeks. Algorithms had to learn to recognize their alien signatures instantly. Machine learning systems were trained on simulations of hypothetical visitors until they could distinguish them from the teeming swarm of ordinary near-Earth objects. The goal was speed identification within hours, global coordination within days. But more than vigilance, astronomers began preparing to strike back with opportunity. Oumuamua had granted them just 11 weeks. In that narrow window they gleaned its size, shape, trajectory, but its true composition, its internal structure, its origin, those slipped away. Next time, they vowed, would be different. Protocols were drafted, telescopes pre-assigned time, rapid response spectroscopy at the ready, radar imaging scheduled in advance. Space agencies drew up proposals for intercept missions. JAXA, the Japanese space agency, studied solar sails that might chase down such visitors. At NASA's Jet Propulsion Laboratory, engineers debated whether existing spacecraft could be retasked to rendezvous with one. The search broadened. Infrared telescopes recalibrated to spot the heat signatures of dark wanderers invisible to optical eyes. Radio astronomers developed methods to detect ultra-faint outgassing, invisible in spectra but audible in frequency. Even gravitational wave scientists speculated whether their instruments might pick up tremors from massive intruders passing through. And as the instruments evolved, so too did the questions. If interstellar debris was common, it represented not just astronomy, but astrobiology, not just physics, but philosophy. Perhaps these objects carried complex organic molecules, forged in alien chemistries. Perhaps they carried spores, or dormant microbes, seeds of panspermia scattered across the galaxy. Suddenly, the ancient idea that life might travel star to star felt less like speculation and more like possibility. Astrobiologists began drafting protocols for sterilized sample return missions. Ground-based spectroscopists refined their tools to hunt for biosignatures, molecules that could hint at living chemistry embedded in stone. SETI, too, shifted. For decades it had listened for radio beacons. Oumuamua suggested another possibility. Civilizations might prefer messengers of stone and alloy, physical artifacts adrift between stars. The idea was radical, but not dismissed. New protocols mandated that every confirmed interstellar object would be scanned for anomalous radio emissions, unusual reflectivity, or optical patterns suggesting artificial design. The sky might be filled with silent probes, their signals encoded in structure rather than broadcast. The transformation of astronomy was profound. A field once limited to modeling the hypothetical now possessed data from a real interstellar visitor. Almost overnight, a new discipline was born: interstellar object science. Conferences were convened, journals created, young researchers carving careers in a field that hadn't existed before 2017. And yet beneath the flood of preparation and technology, a deeper current moved: philosophy. For the first time, humanity understood itself not as an isolated observer, but as a participant in a galactic exchange. Our solar system was not sealed off by light years. It was porous, permeated by fragments of other worlds. The age of interstellar archaeology had begun. Each new visitor would carry a shard of history material flung outward by alien cataclysms, frozen remnants of planetary birth, or perhaps relics of intelligence. Studying them would allow us to reconstruct the larger narrative of the galaxy itself: how worlds form, how they die, how matter migrates across the abyss. And so the stage was set. Automated surveys scanned the night sky without pause. Algorithms sharpened their vigilance, parsing motion patterns in real time. Space agencies refined intercept mission designs. Philosophers and scientists alike leaned forward, waiting. The question was no longer if another messenger would come. The question was when. Somewhere in the darkness beyond Neptune, perhaps already on its inward trajectory, the next object was on its way, and when it arrived, humanity would not be caught unprepared. We would be waiting, instruments ready, our minds sharpened by humility and wonder. The night of the 19th of October, 2017, had been the end of one era, the age of ignorance about interstellar wanderers. What followed was the beginning of another, an era of vigilance, anticipation, and discovery. A new cosmic era. Part 5. Enter 3I Atlas, the second messenger. The 1st of July, 2025. At Rio Hurtado in Chile, the Atlas telescope performed its nightly survey, scanning the crowded fields of Sagittarius. For hours the data looked routine, the endless rhythm of stars fixed in their ancient places. But then the algorithms flagged something strange: a faint speck barely above the noise floor, yet moving with the wrong speed, in the wrong direction, to belong to our solar system. At 3:47 a.m. local time, Dr. Larry Deneau, principal investigator of ATLAS at the University of Hawaii, received the alert. After years of watching near-Earth asteroids skim past our planet, his team knew instinctively when something didn't fit. This one, designated C divided by 2025 N1, Atlas, was different. The orbital solutions, ready just 6 hours later, electrified the global astronomy community. An eccentricity near 6.0 proof of a hyperbolic trajectory. Relative velocity, 61 kilometers per second, the fastest confirmed interstellar visitor yet. And this time, unlike with Oumuamua, astronomers had the gift of foresight. The discovery came months before perihelion. Instead of scrambling, they had time precious months to observe. The designation followed the usual rules: C for comet, 2025 N1 for the first object discovered in the second half of July, and Atlas for the discovering survey. Later, it would earn the title 3I Atlas, the third confirmed interstellar object after 1I Oumuamua and 2I divided by Borisov. Already, 3I Atlas was rewriting expectations. Even at 4.5 astronomical units out near Jupiter's orbit, it showed activity. A faint coma of gas and dust, a stubby tail stretching 25,000 kilometers. This was no silent rock. It was alive with sublimation. Its volatile compounds stirred long before reaching the inner solar system. The Gemini North Telescope on Mauna Kea captured the first high-resolution images. A glowing haze, comet, like in every sense, a contrast to Oumuamua's dry, star-like appearance. Within 48 hours of the announcement, the world's instruments converged. The Very Large Telescope in Chile trained its spectrographs. Hubble was retasked to image the nucleus and coma in ultraviolet detail. Radio telescopes swept the skies for artificial signals, standard protocol now, though none were found. Unlike the chaos of 2017, this time the response was seamless. Years of preparation had borne fruit, telescope time pre-allocated, coordination channels established, instruments calibrated. As Dr. Robert Werrick, discoverer of Oumuamua, remarked, "We learned our lesson. This time we were ready." Early spectra revealed a nucleus dominated by silicate minerals and organic compounds, not unlike comets from our own Kuiper belt. But isotope ratios told another story. Chemical fingerprints inconsistent with our sun's neighborhood, pointing instead to a system of different metallicity, a different stellar past. Here was matter born beneath an alien sky. Its rotation period, about 29 hours, was unremarkable, slow compared to Oumuamua's frenetic tumbling. Its light curve suggested a near-spherical body or modest elongation, nothing like the impossible cigar shape of its predecessor. On the surface, 3I Atlas looked ordinary, what astronomers had always expected interstellar comets to be. But appearances quickly unraveled. As the object fell inward, strange behaviors emerged. Outgassing waxed and waned in irregular cycles, not strictly tied to solar heating. Spectral lines flickered, chemical signatures appearing and disappearing, as if stratified layers of ice and rock were sublimating in sequence. Its tail showed asymmetries, hinting at complex rotation or perhaps fractures hidden beneath the coma. What looked simple at first was in fact a laboratory of alien chemistry in motion. The significance was enormous. 2 interstellar visitors in just 8 years after centuries of seeing none meant the galaxy was teeming with such objects. Statistical models recalculated with updated detection efficiencies now predicted several pass through the inner solar system each decade, and their arrival directions told a deeper truth. While Oumuamua, had swept in from Lyra, near Vega. 3I Atlas arrived from Sagittarius, nearly 90 degrees apart in the sky. The message was clear. These were not rare alignments. The galaxy was sending objects from all directions, a population truly galactic in scale. Its velocity, 61 kilometers per second, posed another mystery. Faster than most ejected debris, it hinted at violent origins. Perhaps it had been hurled outward by a supernova shock, or flung from a system destabilized by a dying star. Simulations traced possible birthplaces across millions of years, through the gravitational tugs of countless stars. Early results suggested the galactic thick disk, a region of older stars, metal poor, shaped by chaotic encounters. If true, 3I Atlas carried in its dust the chemistry of stars that predated our Sunday. The media, wiser now, tempered their headlines. Gone were the sensational whispers of alien probes. Instead, coverage focused on the profound scientific opportunity, the first chance to study, in detail, pristine material from another planetary system. Astronomers emphasized its natural identity while marveling at the gift it represented. Yet beneath the measured tone lay awe. Each interstellar visitor was more than debris. It was a sample return mission conducted by nature. Oumuamua had given us mystery. Borisov, a brief cometary glimpse. Now, 3I Atlas offered time, clarity, depth. Its isotopes and minerals told of processes in another star's nursery. Its volatile ices spoke of chemistry beyond the sun's reach. Its behavior carried the fingerprint of a history unshared by any world we knew. As it approached perihelion 1.4 astronomical units, scheduled for the 30th of October, 2025, anticipation swelled. Observatories readied spectrographs and radars. Agencies debated whether a spacecraft intercept might be possible. Astrobiologists whispered about panspermia, about whether complex molecules, perhaps even precursors of life, were hidden in its ices. SETI scientists tuned their receivers, knowing the odds were slim, but unwilling to ignore the possibility that some artifacts in this cosmic stream might be deliberate. The larger meaning was unmistakable. These objects were not accidents. They were inevitable, the natural byproduct of planetary birth and death across the Milky Way. They arrived not once in a lifetime, but regularly, from every direction, carrying fragments of alien histories. Our solar system was not isolated. It was open, porous, part of a galactic ecosystem. Oumuamua had forced us to ask if we were alone. 3ATLAS gave us something subtler, but just as profound. Proof that our skies are connected to other worlds in the most literal way. The messengers come unbidden, carrying chemistry, physics, and stories we cannot yet fully read. And so the second messenger, brighter and more revealing than the first, continued its journey inward. By late autumn, it would blaze near the sun, its coma expanding, its secrets laid bare to every instrument humanity could point its way. And when it turned outward once more, vanishing into the deep black, it would leave behind a record, a data set, a story, a legacy that would echo across astronomy for decades. The era of interstellar visitors had not ended with Oumuamua. It had only just begun. Part 6. The Path of the Outsider. The trajectory of 3I Atlas was more than a curve plotted on paper. It was a narrative written in the language of gravity, geometry, and time. Every point on its hyperbolic path was a sentence in a story that stretched across millions of years and countless light years of interstellar space. To glimpse where this wanderer was going, astronomers first had to ask where it had been a cosmic detective story unfolding across the galaxy. Unlike the closed ellipses of planets or the stretched ovals of comets bound to the sun, 3I Atlas traced a hyperbola with an eccentricity near 6.0. In orbital mechanics, anything above 1.0 spells exile, an unbound trajectory, proof that this object had not been born under the Sun's dominion and would not remain here after its fleeting passage. Its perihelion, scheduled for the 30th of October 2025, would bring it to within 1.4 astronomical units of the Sun, roughly the orbit of Mars. Close enough for exquisite observation, yet far enough to avoid total incineration. Its nearest pass by Earth would be a comfortable 1.6, 1.8 AU, safe but scientifically tantalizing, yet the real intrigue lay not in distance, but in direction. 3. I Atlas had entered from Sagittarius, plunging into the solar system at a steep angle nearly perpendicular to the plane where planets circle. This sideways approach was rare and revealing. It hinted at a history shaped by the complex flows of galactic debris rather than any local kinship to our star. To reconstruct its origin, supercomputers ran simulations both forward and backward in time, accounting for the gravitational nudges of every nearby star over millions of years. The effort strained even the most advanced codes. Dr. Feiho Feng of the University of Hertfordshire likened it to solving a cosmic murder mystery where the crime scene is millions of years old and scattered across hundreds of light years. Every star is a suspect, and the evidence has been blurred by eons of interference. The object's velocity was another clue. 61 kilometers per second relative to the Sun, faster than most ejected debris. Such speed implied violence. Perhaps it had been flung by a giant planet's slingshot, the way Jupiter ejects comets from our system. Or maybe it was expelled during the death throes of its parent star by stellar winds, gravitational upheavals, or even a cataclysmic explosion. Another possibility: acceleration through encounters with massive bodies across a journey spanning millions of years. Whatever the mechanism, its motion bore scars of turbulence and force. Comparisons sharpened perspective. Oumuamua had arrived from Lyra, 2I divided by Borisov from Cassiopeia, and now 3I Atlas from Sagittarius. 3 directions separated by nearly right angles. This triangulation told a larger truth. Interstellar visitors arrive from all quarters. The Milky Way is not a still ocean but a turbulent river, filled with flotsam from shattered planets and dying suns. The galactic context deepened the revelation. Our Sun orbits the Milky Way at 220 kilometers per second, completing a revolution every 225 million years. During its own million-year journey, 3I Atlas would have crossed the wakes of dozens of stars, each encounter altering its course by imperceptible but cumulative degrees. Its isotopes, meanwhile, whispered of another birthplace. Spectroscopy showed silicate minerals and organic compounds like those in comets here, but isotope ratios diverged subtly, pointing to formation around a star with different metallicity. Perhaps an older, metal-poor star. Perhaps a younger one seeded by earlier supernovae. Its inclined approach relative to the galactic plane suggested an origin in the thick disk, a population of older stars with distinct chemistry and motion compared to the thin disk where our Sun resides. If true, 3I Atlas carried in its nucleus the geology of another epoch of the galaxy samples forged before our Sun was even born. And what of its future? After October's perihelion, the object would arc outward again, gradually regaining speed until it crossed the outer planets and slipped beyond Neptune by early 2026. Its outbound trajectory aimed toward Perseus, predictable for a few thousand years before gravitational encounters once more scrambled the record. By then, its surface would carry subtle alterations: solar heating scars, sputtered radiation tracks, Should it one day wander through another star system, alien astronomers might read in those markings the fingerprint of its brief encounter with our Sunday. The precision of orbital mechanics offered humanity a gift that Oumuamua had denied: foresight. Months before closest approach, telescopes could be scheduled, spectrographs calibrated, radars aligned. Even space agencies considered daring proposals for rapid response probes. The European Space Agency quietly ran studies for an interceptor craft, designed to ride a slingshot trajectory and meet the visitor before it fled again into the dark. But the greatest gift of 3I Atlas was not logistics. It was perspective. As it drew inward, astronomers noted the vast scale of its backstory. This object had been traveling since long before the first humans walked upright on the savannah. It carried dust older than civilization, isotopes older than our solar system, and a trajectory sculpted by stellar events we can only imagine. Its path reminded us that the galaxy is not static, but dynamic, a living ecosystem where material flows constantly from system to system. Rocks, ices, and organic matter wander across light years, weaving a silent web of exchange. In that sense, every interstellar visitor is a time capsule, a messenger not just from another place but from another era. Every precise measurement of 3I Atlas, its velocity, its spin, its chemical spectrum was more than data. It was a verse in the poem of galactic history. Each number added to a narrative of birth, ejection, exile, and survival. A narrative that would continue long after our sun exhausts its nuclear fuel. And so the outsider moved on, tumbling through the dark, briefly illuminated by starlight we call our own. It carried secrets from beyond our horizon, messages carved into silicates and ices, fragments of a cosmic story we are only beginning to decipher. Part 7. Signals in the Noise. 3 interstellar visitors, 3 completely different personalities. By mid-2025, as 3I Atlas drew deeper into the solar system, astronomers found themselves running comparisons lining its every twitch, flare, and emission against the 2 enigmas that had come before. They were no longer studying single anomalies, but a small, growing family of outsiders. The hope was simple: to find patterns in their behavior, signals hidden within the noise, that could reveal universal truths about the objects that wander between stars. The differences were stark. Oumuamua, discovered in 2017, had been utterly inert. No coma, no tail, no whisper of volatile activity, even though it had swung to within 0.25 AU of the Sun, where water ice should have boiled off in torrents. By contrast, 3I Atlas started shedding material long before it even reached Jupiter's orbit. Its coma bloomed into a diffuse cloud, nearly 50,000 kilometers across, larger than Mercury, an unmistakable sign of vigorous sublimation. In between stood 2I divided by Borisov, found in 2019, behaving like a textbook comet but with a twist. Exotic chemistry, including carbon monoxide concentrations 10 to 50 times higher than any comet native to our system. Dr. Alan Fitzsimmons of Queen's University Belfast, who had studied all 3, framed the mystery memorably. It's like receiving 3 postcards from different countries, written in completely different languages, yet all describing the same basic experience of travel. Morphology underscored the diversity. Oumuamua's bizarre form, possibly 10 times longer than wide, had no natural parallel we could find. Its chaotic tumbling and unexplained acceleration still defied complete explanation, years after it vanished. 3I Atlas, in contrast, appeared almost pedestrian. Its light curve pointed to a near-spherical body, or at most elongated by a factor of 2. Its rotation period of 29 hours was unremarkable, its axis steady. Borisov had fallen somewhere in between, slightly elongated, with a stable spin around 7 to 8 hours. 3 objects, 3 geometries, none conforming to a single archetype. The chemical signatures told equally divergent stories. Borisov had carried water vapor, carbon monoxide, cyanide, the familiar ingredients of comets, yet in ratios unlike anything catalogued locally. Its birthplace had clearly been a cold, outer system orbiting another sun-like star. Atlas added another layer of strangeness. Spectra revealed silicates and organics, a rocky heart beneath layers of volatile ice. Its isotope ratios for hydrogen, oxygen, and carbon deviated subtly from solar norms, indicating a star with different metallicity and evolutionary history. The coma contained complex organics, weathered by cosmic rays during millions of years of exile. Rotation and dynamics added further texture. Oumuamua spun every 8 hours, but did so chaotically, as if unbalanced or fragmented within. Its endurance under such stresses suggested either extraordinary tensile strength or structural reinforcement, prompting some to wonder about artificial origins. Borisov's conventional spin aligned with expectations for an icy nucleus. Atlas rotated more slowly, suggesting greater mass or stronger cohesion. Subtle rhythms in its outgassing synchronized with this rotation, revealing patches of volatile rich terrain, a geological map written in vapor. Outgassing itself highlighted the extremes. Oumuamua's silence had fueled endless speculation about hydrogen icebergs, fractal dust, or alien construction. Borisov's activity, by contrast, was vivid and predictable. Bright tails, steady decline as it retreated, a model of cometary behavior. Atlas, meanwhile, broke the mold again. It began venting far earlier than theory predicted, and its patterns were irregular, hinting at internal processes or structures unlike any comet we had studied. Speed became another axis of comparison. Oumuamua entered at 26 kilometers per second relative to the Sun, suggesting a modest ejection, perhaps by giant planet dynamics from a nearby star system. Borisov, faster at 32 kilometers per second, implied either a more distant origin or more energetic ejection. Atlas shattered expectations at 61 kilometers per second. Such velocity demanded catastrophe, a stellar explosion, a close brush with a black hole, or a long acceleration through encounters across the galactic thick disk. Its speed alone marked it as an emissary from far beyond the Sun's familiar neighborhood. Taken together, the trio painted a sobering portrait. Where once astronomers assumed interstellar debris would be broadly similar, dirty snowballs wandering the void, the reality was chaos and diversity. One silent, elongated rock, one textbook comet with exotic chemistry, one vigorous, rocky icy hybrid venting unpredictably at record speeds. Population statistics shifted overnight. 3 detections in less than a decade implied that the inner solar system was crossed by such visitors several times each decade. Most slipped by unseen, too small or faint for our surveys. Extrapolated across the galaxy, this suggested a staggering reservoir, perhaps trillions of wanderers larger than 100 meters, drifting endlessly between stars. Some would be pristine fossils of planetary birth, others wreckage from catastrophic collisions or stellar deaths. Computer models pushed the speculation further. Future detections might include vast icy giants hundreds of kilometers across, or tiny, dense fragments of exotic minerals. Some might carry frozen organics unaltered since the dawn of their systems. A few might even, as some dared whisper, embody something crafted structures meant to endure interstellar time. Dr. Robert Werrick, discoverer of Oumuamua and later Borisov, reflected on the transformation. We've gone from 0 to 3 detections in under a decade, and every one of them is different. That means the larger population is more diverse than we ever dared imagine. Each visitor is a sample from another corner of the galaxy, carrying its own unique story of creation, evolution, and ejection. The implications cascaded. The chemical diversity told us that planetary systems evolve under profoundly different conditions, producing unique chemistries. The spread of velocities revealed that no single ejection mechanism suffices. Multiple pathways populate interstellar space. And most importantly, the sheer frequency of arrivals showed that material exchange between stars is constant, not rare. The galaxy is not a static museum of isolated systems, but a living ecosystem where matter flows ceaselessly. By 2025, the scientific community had accepted the new paradigm. The space between stars is not empty but crowded, alive with messengers. Each visitor adds a line to the growing text of interstellar archaeology. We are piecing together, fragment by fragment, the story of worlds we may never visit directly, as 3I Atlas surged inward, feeding our instruments with fresh data every night. One truth crystallized. These were not isolated anomalies, but the opening chapters of a much larger saga. We had begun to hear the signals in the noise. The messengers would keep coming, and with each one, our understanding of the galaxy and our place within it would deepen. Part 8. The probability problem. The mathematics were troubling. That was the cautious phrase astronomers used, though in private conversations many admitted the truth was far harsher. The numbers didn't just look wrong, they shattered decades of assumptions. Before 2017, before the sudden appearance of Oumuamua, the best simulations had predicted that interstellar visitors large enough to detect would grace the inner solar system perhaps once in a century. 100-year wait, if luck was on our side. Yet less than 8 years later, the count stood at 3 Oumuamua, 2I divided by Borisov, and now 3I Atlas. Models weren't off by a factor of 2 or 3, they were off by 10, by 100. Dr. Alan Stern of the Southwest Research Institute admitted as much at a 2025 conference. We weren't just wrong, we were spectacularly, embarrassingly wrong. His earlier estimates, bold for their time, had suggested maybe one detection per decade with the best telescopes. Reality had humbled him and everyone else. The crux of the problem lay in foundational assumptions about how planetary systems shed material. Classic theories imagined ejections as rare, confined mostly to epochs of planetary migration, like our own solar system's late heavy bombardment, billions of years ago, when giant planets shuffled into place. That model implied a trickle of debris, not a flood. But the new discoveries demanded another story. Either ejections were far more common than imagined, or their efficiency at producing large, detectable bodies was wildly underestimated. The implications rippled outward, touching not just astronomy, but galactic dynamics itself. If these 3 messengers represented an average sample, then dozens of similar bodies might pass through our neighborhood every year. Most would slip past unseen, too faint or too fast. But the statistical extrapolation was staggering. Trillions of interstellar objects, larger than 100 meters, drifting through the Milky Way. Collectively, their mass might rival the sum of all planets orbiting all stars combined. Detection patterns added to the puzzle. Each of the 3 confirmed interstellar objects had been caught not by the grandest instruments, but by modest, automated survey telescopes, pan-stars, amateur-scale rigs, and Atlas. This suggested that as larger facilities like the Rubin Observatory came online, detection could become routine, even monthly. Dr. Robert Jediker of the University of Hawaii described the strangeness. It's like birdwatchers who searched for decades without a sighting, then suddenly spotted 3 rare species in 1 week. Either we're impossibly lucky, or the sky is thick with birds we never learned how to see. Biases made the math trickier. Interstellar objects are easiest to detect when they pass near Earth, moving slowly enough for repeat imaging. Others slip behind the dense star fields of the Milky Way, or arrive from directions obscured by solar glare. Monte Carlo simulations, generating millions of hypothetical wanderers, consistently concluded that to match our actual detection rate, the underlying population had to be orders of magnitude larger than believed. Where did they all come from? Theories multiplied. Stellar flybys, once thought relatively harmless, might actually eject swarms of debris each time 2 stars brushed past within a few thousand astronomical units, a scenario likely for every system on million-year timescales. Binary stars, which make up half the galaxy's population, could hurl planets and comets into the void as they evolved and destabilized. Supernovae and other cataclysmic deaths of stars might blast entire systems into fragments, creating high-velocity projectiles like Atlas. Another factor was gravitational focusing. The sun itself bends the paths of passers-by, funneling them inward. This subtle lensing might artificially boost the rate we observe, making our system a preferential target zone rather than a random sample. Some researchers thought even bigger. Galactic tides, the gravitational pull of the Milky Way's spiral arms, its bar-shaped bulge, and its dwarf galaxy companions could periodically disrupt vast regions, sending waves of debris washing across interstellar space. If true, humanity's first detections might not be random luck, but the crest of such a wave. The timing gnawed at astronomers. Why now, during the narrow window of human technological adolescence? The anthropic principle offered one answer. Perhaps we exist in a galactic region or epoch where the flux of interstellar objects is naturally high. Or perhaps, as Dr. Avi Loeb of Harvard suggested, some fraction of these bodies were not natural at all. If civilizations exist, he argued, and if they sometimes launch probes, sails, or artifacts into interstellar space, then the population we observe could be a blend, natural debris and artificial messengers alike. Controversial, yes, but Oumuamua's unexplained elongation and acceleration lingered in memory as data points without satisfying natural explanations. The probability problem spilled into astrobiology as well. If trillions of objects wander the galaxy, then each is a courier. They may carry organic molecules, frozen chemistry, even microbial life sealed in rock or ice. The panspermia hypothesis, life seeded across stars by natural transport, suddenly gained teeth. Complex organics detected in Borisov and Atlas seem to confirm the idea that interstellar space is not barren but rich, a medium for exchange. Planetary defense felt the tremors too. If such bodies pass the inner solar system multiple times per decade, then even if impact probabilities remain tiny, the long-term risk must be recalculated. Earth's geological history may hide scars from interstellar strikes, their traces long since eroded. As Rubin, Gaia's successor, and other instruments sharpened their gaze, candidate detections began arriving with increasing frequency. Humanity stood at the edge of an observational cascade. The universe, once imagined sparse, was revealing itself as crowded, dynamic, alive with motion. The mathematics of chance had been rewritten by observation. What we had thought improbable was now routine. The space between stars was no longer an abyss of emptiness, but a thoroughfare, an ocean crossed by endless flotsam. Wanderers moved constantly between systems, each carrying within it the memory of another world, another star, another time. The probability problem was not merely a scientific embarrassment, It was a revelation. The galaxy was far more interconnected than we had dared imagine, and we had only just begun to recognize the signals hidden in the cosmic noise. Part 9. The Fermi Paradox Revisited. Where is everybody? Enrico Fermi's deceptively simple question, voiced over lunch in 1950, had long haunted the scientific imagination. For decades, it framed the silence of the skies. If the galaxy holds billions of stars and countless habitable planets, then why have we found no evidence of other civilizations? The paradox rested on assumptions of emptiness. Space was thought to be vast, barren, and hostile. Signals would fade, probes would be rare, and travel would demand resources even advanced civilizations might balk at spending. But by 2025, that framework was in tatters. Oumuamua, 2I divided by Borisov, and 3I Atlas had rewritten the picture. Interstellar space was not an abyss but a river of debris, a ceaseless current of objects migrating between stars. If natural messengers could wander so freely, why not artificial ones? Statistics sharpened the point. Bodies larger than 100 meters were now estimated to pass through the inner solar system several times per decade. Scaled down to smaller fragments, this implied thousands of interstellar grains and shards raining through Earth's skies every year, most too small to survive entry or too faint to notice. The Fermi question no longer felt like a search for signals. It felt like a question of recognition. What if the messengers were already here, but we had failed to read them? Dr. Avi Loeb of Harvard was blunt. We've been listening for radio signals for decades, but maybe advanced civilizations prefer to send objects. A single artifact can carry more information than any broadcast, and it guarantees delivery. The idea was not science fictions alone. For decades, theorists had speculated about Bracewell probes, self-replicating messengers, drifting between stars, storing and transmitting knowledge. Now, with 3 very different interstellar visitors on record, the idea no longer seemed fanciful. The difficulty was in distinguishing artifact from asteroid. Oumuamua's extreme elongation, inexplicable acceleration, and silence defied neat natural explanations. Yet most astronomers clung to cometry models stretched beyond comfort. Occam's razor, the demand for extraordinary evidence, and the fear of false discovery all pulled science toward caution. But as more visitors were found, the statistical argument itself began to shift. If purely natural, the odds of us detecting 3 in such quick succession during humanity's fleeting technological adolescence seemed vanishingly low. Loeb calculated the chance at roughly 1 in 10,000. Perhaps luck, or perhaps not. SETI researchers adjusted. Newly discovered visitors were scanned automatically for radio signatures, optical glints, or surface reflectivity inconsistent with natural rock and ice. Proposals grew bolder. ESA floated concepts for intercept probes that could rendezvous with the next suitable interstellar visitor. A single close-up inspection might decide the matter. Was this simply ice and dust, or was it something more? The implications reached beyond living civilizations to what some began calling galactic archaeology. If technological species had been scattering artifacts for millions of years, then some of the wanderers entering our solar system could be fossils of intelligence long extinct. These objects, if ever decoded, might carry cultural records, technologies, even cautionary tales from civilizations erased before Earth's sun was born. The Milky Way could be a museum, its galleries drifting unnoticed until we learn how to see them. And what of us? Humanity had already launched its first artifacts into interstellar space, the Voyagers, Pioneer plaques, New Horizons. Long after Earth is gone, these will drift between stars, silent emissaries of our species. Less noble debris spent rocket stages, defunct satellites, will eventually leak outward as well. Future alien archaeologists might judge our era not by golden records but by the junkyard we left behind. Philosophically, the shift was seismic. The Fermi paradox no longer asked why the galaxy was silent. It asked whether we had been listening in the wrong way. If interstellar space is thick with material exchange, then where is everybody? May already have an answer, all around us, in forms we barely recognize. This reimagining expanded the search for extraterrestrial intelligence. Radio astronomy remained important, but now it was only one instrument in a larger orchestra. Interstellar objects became central to the score. Every trajectory, spectrum, and rotation curve a potential message. A visitor's structure, its chemistry, even its improbable velocity, could encode intention. Unlike beacons, which announce themselves loudly, artifacts might be designed to hide, to appear natural, avoiding destruction by hostile species. Recognizing them might require a new science of subtlety. The paradox thus became less about silence and more about interpretation. The galaxy may be communicating constantly through physical messengers rather than electromagnetic waves. Our task is not merely to listen, but to learn how to read. Each detection, Oumuamua's enigma, Borisov's chemistry, Atlas's furious activity was a sentence in an unfolding galactic dialogue. The loneliness of earlier centuries, the assumption that stars were islands cut off by void, was dissolving. In its place rose a new awareness. We live within a network, an ancient circulation of matter and maybe meaning, tying civilizations across epochs. Whether those civilizations endure now, or only their artifacts survive, is an open question. The answer to Fermi's riddle may not be that the galaxy is empty, but that we are only just beginning to notice its voices. Perhaps they have always been here, carried not on waves of radio but on the paths of wanderers, drifting silently into our skies, waiting for us to see. Part 10. Theories, Tensions. The coffee on Dr. Sarah Chen's desk had gone cold long ago, but she hardly noticed. At the Jet Propulsion Laboratory, her eyes stayed fixed on the spectroscopic stream pouring across her monitor data from 3I Atlas that made no sense. The isotope ratios simply did not fit. They didn't match any known models of stellar nucleosynthesis. Either this object had formed in conditions utterly alien to anything we'd ever seen, or the foundations of astrophysics itself were overdue for rewriting. She was not alone in her unease. Across the global astronomy community, the growing catalogue of anomalies in interstellar visitor data had carved scientists into opposing camps. On one side stood the methodological conservatives, insisting that natural explanations must be exhausted before even whispering alternatives. On the other, an increasingly vocal group argued that the accumulating evidence was too strange to ignore, and that hypotheses dismissed as science fiction now deserved serious consideration. Oumuamua remained the lightning rod. 8 years after its 2017 discovery, its mysteries still rankled. No simulation tidal disruption by massive stars, catastrophic collisions in stellar nurseries, exotic sublimation could reproduce its extreme elongation, rapid tumbling, and subtle non-gravitational acceleration all at once. Something didn't add up. Dr. Alan Fitzsimmons of Queen's University Belfast spoke for the cautious camp. Science advances by finding natural explanations for natural phenomena. History is full of mysteries that seem to demand exotic answers until we understood them. For him, Oumuamua was unusual, but unusual did not mean artificial. Conservatives clustered around increasingly baroque natural hypotheses. Perhaps it was a block of solid hydrogen, venting invisibly as it warmed. Perhaps it was a nitrogen iceberg, chipped from the frozen crust of a Pluto-like world. Exotic, yes, but still within the known laws of chemistry and physics. Dr. Avi Loeb of Harvard became the champion of the opposite view. When you're forced to invoke invisible outgassing, never seen before materials, and unobserved formation mechanisms, maybe it's time to entertain the simpler explanation: technology. For Loeb, artificiality was no longer the extraordinary claim. The convoluted natural explanations had become extraordinary in themselves. The argument quickly transcended astronomy. It cut to the heart of how science works: the burden of proof, the risks of intellectual conservatism, the danger of sensationalism. Dr. Michelle Bannister of the University of Canterbury struck a middle note. The real issue isn't whether one object is natural or artificial. The issue is that our models are incomplete. Planetary formation, stellar evolution, interstellar chemistry, something fundamental is missing. Media attention only poured fuel on the fire. Headlines screamed, "Alien probe," and researchers scrambled to downplay such claims, fearful of being caricatured as crackpots. The defensive posture hardened into silence. Conversations that once filled hallways at conferences were now whispered privately, if at all. The history of astronomy provided uncomfortable parallels. In the 1960 seconds, the first pulsar signals, eerily regular radio pulses, were jokingly dubbed LGMs, little green men. Only later, after multiple detections, did the field accept them as neutron stars. But unlike pulsars, interstellar visitors offered no second chances. They appeared, lingered for weeks or months, and vanished forever into the dark. That brevity deprived science of the long timelines needed to build consensus. Scientific culture itself played a role in suppressing speculation. Peer review favored incremental progress over radical leaps. Grants flowed towards safe projects, not to risky attempts at paradigm shifts. Careers thrived on building upon established frameworks, not challenging them. Junior scientists, in particular, felt trapped. Dr. Jennifer Bergner of UC Berkeley admitted, "I've seen young researchers censor themselves. They fear being labeled fringe if they even suggest artificial possibilities. We're silencing our best questions before they're asked." International differences compounded the strain. European institutions leaned conservative, emphasizing methodological rigor. American scientists, less bound by hierarchy, floated wilder ideas in public. Asian researchers often found themselves bridging the two extremes. Social media amplified everything. Speculative tweets about alien origins went viral, while sober analyses of natural processes languished unread outside professional circles. The polarization spilled into telescope allocation. Committees faced proposals split down ideological lines. Some demanded conventional cometary observations. Others wanted explicit searches for artificial signatures. In response, certain facilities quietly discouraged projects framed in terms of alien technology, preferring neutral studies that could yield publishable results either way. Generational divides sharpened the edges. Senior researchers, with careers built on classical models, resisted explanations that might undercut decades of work. Younger scientists, less invested, leaned toward openness. Dr. Robert Werrick, discoverer of both Oumuamua and 3I Atlas, embodied the dilemma. "I spent my career expecting asteroids and comets. Then I found objects that broke every category. It forces you to question everything you thought you knew." With each new interstellar object, the data piled higher. Borisov's bizarre carbon monoxide excess. Atlas's isotope ratios that mocked current models. Oumuamua's impossible geometry. No single natural framework seemed able to stretch wide enough to fit them all. But neither could anyone prove artificial origins. The tension sat unresolved, a scientific culture caught between fear of error and fear of missing truth. Late at night, in conference bars and quiet labs, astronomers found themselves asking questions once unthinkable. How would we recognize alien technology? What signatures would distinguish artifact from anomaly? And if we did find such proof, how should science and humanity respond? Theories proliferated. Perhaps interstellar objects were diverse enough that no single model would explain them. Perhaps artificiality accounted for only a fraction of the population. Perhaps the boundary between the natural and the engineered was itself fuzzier than we imagined. The debate exposed science's deepest fault line, the line between skepticism and imagination. Cross it too easily, and credibility collapses. Refuse to cross it at all, and discovery slips through your fingers. Meanwhile, the objects themselves continued their ancient journeys, indifferent to our arguments. Oumuamua tumbled away toward Pegasus. Borisov faded back into the dark. Atlas roared closer to the sun, spilling secrets into spectrographs that refused to align with our models. Each visitor carried with it data that unsettled the neat frameworks of the past, demanding theories bold enough or humble enough to admit how much we still do not know. And so the tensions endured. Laboratories buzzed, committees argued, reputations trembled, but the messengers from the stars went on arriving, silent and unanswerable. Whether the truth lay in exotic chemistry, in physics yet to be uncovered, or in technologies seeded by other minds, one fact became undeniable. The cosmos was stranger, richer, and more dynamic than anyone had dared imagine. The cold coffee sat forgotten, but the data streamed on. Humanity had entered a new scientific era, one defined as much by its debates and doubts as by its discoveries. The theories multiplied, the tensions deepened, and somewhere, in the background noise of the universe, the next messenger was already on its way. Part 11. The next discovery could change everything. High in the Chilean Andes, the Vera C. Rubin Observatory was humming with final tests. Its giant 8.4-meter mirror and 3 billion pixel camera, designed to map the entire night sky, were coming online months ahead of schedule. The urgency was clear. The galaxy was sending messengers, and humanity needed better eyes to catch them. Where earlier generations had relied on chance and favorable geometry, Rubin promised a new era of certainty. Once fully operational, it would scan the visible sky every 3 nights, producing 20 terabytes of data per evening. Its sensitivity reached down to 24th magnitude, 40 million times fainter than the dimmest stars visible to the naked eye. Dr. Mario Juric, overseeing its data management systems, explained what this meant. We're moving from 1 detection per decade to dozens per year. Instead of scrambling to catch objects as they leave, we'll follow them from the moment they arrive. The implications were staggering. Rubin would widen the net beyond Earth's immediate neighborhood, detecting wanderers still far from the Sunday. This meant months, sometimes years, of preparation before closest approach. No longer would interstellar visitors appear as sudden, fleeting enigmas. They would become long-studied travelers, tracked across time. Artificial intelligence would be essential. Machine learning systems, trained on millions of simulated orbits, were being designed to sift through billions of detections each night, separating hyperbolic paths from the common elliptical swarms of asteroids and comets. Within hours of a candidate appearing, alerts would ripple across the globe. European Space Agency networks would trigger automatic follow-ups. Observatories in Hawaii, Chile, and South Africa would align their instruments in coordinated campaigns. But detection was only the first step. The true revolution lay in statistics. With hundreds, perhaps thousands, of interstellar visitors catalogued, astronomers could at last search for patterns invisible in individual anomalies. Do isotope ratios cluster by stellar metallicity? Do spin rates reveal universal processes of formation and ejection? Do the velocities tell us whether most are born in quiet planetary migration or in cataclysmic stellar deaths? NASA's Jet Propulsion Laboratory was preparing to go further still. Engineers sketched concepts for rapid response interceptors, solar, sail craft capable of riding sunlight to extraordinary speeds, or slingshot maneuvers that might let them rendezvous with objects streaking at 50 kilometers per second. The payoff would be immense, said Dr. Julie Castillo Roguez, leading JPL's interceptor studies. Direct sampling could reveal formation, chemistry, cosmic, ray damage, even preserved biological material. The prospect of holding in a lab a fragment from an alien star system drove mission designers to think at the limits of physics. And there was always the more tantalizing possibility. What if something turned up that wasn't natural? Rubin's flood of data meant that if even a fraction of these wanderers were artificial artifacts from other civilizations, they would become impossible to ignore. Where a single Oumuamua could be dismissed as coincidence, a statistical pattern would demand a different explanation. Search strategies were expanding to meet that possibility. Radio telescopes would now automatically scan new interstellar objects for structured emissions. Optical observatories were trained to look for anomalous reflectivity or engineered geometries. Infrared telescopes, including the James Webb, could probe for internal heat sources inconsistent with frozen rock and ice. More speculative tools were even being discussed. Gravitational wave detectors sensitive to massive, dense visitors, or neutrino observatories that might catch traces of exotic power sources. Planetary defense experts watched closely as well. While the probability of a collision remained low, the revised abundance estimates forced new calculations. Large interstellar impactors, striking Earth once every few million years, could have nudged the course of evolution. Now humanity faced the real possibility of watching such an object approach in real time. More unsettling was the speculative question: what if the trajectory of an artificial object intersected Earth? Emergency protocols, modeled on asteroid defense procedures, were quietly revised to include contingencies for unambiguously technological visitors. Meanwhile, academia was racing to keep pace. Entire programs were springing up devoted to interstellar visitor science. Graduate students now studied not just planetary formation, but astrobiology, materials analysis, even archaeology skills that might one day interpret artifacts from civilizations long extinct. International cooperation surged. NASA, ESA, JAXA, and others coordinated future missions as joint endeavors, treating interstellar visitors as global resources. Data-sharing agreements were drafted. Even private space companies entered the field, envisioning intercept craft that might harvest interstellar material for science, or perhaps one day for commerce. Legal scholars scrambled to imagine new frameworks. Who owned fragments from another star? How would contamination be prevented? What if an artifact contained information or posed a threat? Culture itself braced for impact. Religious leaders, philosophers, and artists debated what it meant to hold in one's hand a stone born around another Sunday. Even if lifeless, these messengers dissolved the illusion of cosmic isolation, and if artifacts of intelligence appeared, the psychological consequences could be as transformative as the science. The sense of anticipation was electric. Night after night, Rubin's tests rehearsed the coming deluge of data. Around the world, observatories stood ready to respond. Spacecraft concepts lingered on drawing boards, and theorists sharpened their models. The next interstellar discovery was not a question of if, but when. And when it came, it could rewrite not only our understanding of planetary systems, but of life and intelligence itself. The future was arriving at 50 kilometers per second. Somewhere beyond Neptune, another messenger was already on its way, carrying answers to questions humanity had only just learned how to ask. Part 12. Closing the loop. The data streams never sleep. Tonight, as you drift toward dreams, robotic telescopes across 6 continents drink in photons that began their journey millions of years ago. From Chile to Hawaii, from Namibia to the Canary Islands, arrays scan the blackness, algorithms sifting for subtle motions, tiny deviations against the fixed stars that betray the presence of outsiders. Ancient wanderers continue their billion-year odysseys, indifferent to whether our new eyes notice them or not. This story began with a single dot of light in 2017, an object not bound to the sun, sliding silently through our backyard. From that moment, everything changed. 8 years later, after debates, discoveries, and revelations, we now confront a universe far more unruly than we imagined. The space between stars is no void at all. It is a thoroughfare, a galactic highway of debris and perhaps messages, carrying fragments of alien worlds to our doorstep. We know the names of 3 who passed this way. 1I, Oumuamua, impossibly elongated, accelerating without explanation, vanishing into Pegasus like a riddle flung into the dark. 2I, divided by Borisov, a comet more familiar in shape, but carrying exotic chemistry, carbon monoxide in quantities no local comet could match. And 3I, Atlas, still inbound, venting gas long before Jupiter's orbit, promising clarity while spawning yet more questions. Each one was different. Each one bent our frameworks until they cracked. Together they whispered the same truth. The galaxy is alive with movement, tangled in exchanges we once thought impossible. The numbers make it undeniable. If 3 such objects appeared in less than a decade, then dozens must pass unseen through our solar system every year. Too small, too dark, too far from our instruments. But they are there, stone, ice, organics, each carrying a signature from the star that birthed it, the system that ejected it, the journey that scarred it. This knowledge reshapes our sense of place. Earth is not an isolated cradle, walled off by light years of emptiness. We are participants in a galactic ecosystem, bathed in samples from other suns since before our planet formed. Some of those atoms, drifting between stars, may have become part of our oceans, our rocks, our bodies. The galaxy does not just surround us, it runs through us. Implications ripple outward. Models of planetary formation must now account for constant cross-contamination. The origin of life on Earth may have depended on organic compounds ferried across light years. Evolution itself may bear the faint fingerprints of interstellar chance. And in the search for extraterrestrial intelligence, the silence of the radio spectrum suddenly feels less decisive. Perhaps civilizations prefer artifacts, physical messengers able to endure million-year voyages where radio fades into noise. Oumuamua taught us how difficult such recognition might be. Was it natural? Artificial? Our tools could not decide. The line between extremely unusual rock and simple probe proved thinner than expected. And if our instruments cannot yet distinguish one from the other, how many messages have already slipped past us, unread? Science adapts slowly, but it adapts. Funding agencies now bankroll interstellar visitor surveys. The Rubin Observatory will soon scan the sky every few nights, detecting dozens each year. AI systems will flag candidates within hours. Coordinated protocols will activate instant campaigns of spectroscopy, radar, and photometry. Humanity is building, step by step, the infrastructure to study alien matter, not as anomalies, but as routine. A new generation of scholars is emerging, fluent not only in orbital mechanics but in astrobiology, in material science, even in archaeology. They prepare for the possibility that among these messengers will be artifacts, technologies from other minds. International frameworks are forming for how to share data, how to avoid contamination, how to respond if a visitor proves undeniably artificial. And the culture shifts too. The hysteria of Oumuamua has softened into steady awe. When Atlas was announced, the headlines were calmer, but the scientific anticipation was electric. We are adjusting to the truth that interstellar visitors are not singular miracles, but regular chapters in a cosmic dialogue. The next stage will be built not on individuals but on populations, hundreds of visitors catalogued, patterns teased from chaos, compositions that reveal the architectures of alien systems, isotopes that record the history of stars long dead, perhaps even direct sampling missions that will catch a wanderer, touch it, bring back a fragment to Earth. Yet for all our preparation, the most transformative discoveries will likely be those that overturn our frameworks entirely. The universe has already shown its talent for surprise. The messengers may carry codes we do not yet know, how to read messages in their geometry, in their chemistry, in their silence. As you lie in the dark tonight, consider the traffic overhead. Shards flung from planetary collisions. Dust expelled in the winds of dying stars. Ice fractured by gravitational chaos around alien suns. All drifting, intersecting, parting, crossing paths across eons. Occasionally, one falls into our neighborhood, offering us a sample, a story, a question. Some carry the organics of life, preserved across light years. Some hold isotopic clues to stellar alchemy in regions we will never reach. And perhaps a few are crafted artifacts, left by civilizations long extinct, carrying knowledge through the ages like bottled messages across a cosmic ocean. The messengers are indifferent to our debates. They tumble, they sublimate, they accelerate according to laws we are still learning to write down. But they are also generous. They bring us fragments of other worlds, proof of connection, evidence that the galaxy is not distant and still, but intimate and alive. Oumuamua is gone now, tumbling outward at nearly 40 kilometers per second, destined to pass near Ross 248 inches 20,000 years. Perhaps intelligence lives there. Perhaps they will see it and wonder as we have wondered. Atlas, meanwhile, brightens nightly, its gases tracing tales that record the chemistry of its long-dead star. And somewhere, unseen, another messenger is already inbound, set on its path before humanity ever existed, destined to arrive exactly now, in the age when we can finally notice. The age of interstellar visitors has begun. We are no longer alone, no longer spectators isolated in one corner of space. We are participants in a galactic conversation written not in words or signals, but in wandering matter. The loop is closing, and so the final question lingers: what else is already on its way?